it was towards the very end of class, I believe I was talking about the thing you guys are not allowed to ride anymore. In fact, you're not even allowed to be in the mall anymore. I find that to be completely ridiculous. But okay.
See if they kick me out today.
I hope that they don't. But I'm still going to have to use this idea that perhaps some of you have been on a carousel. Is there anybody in the room who's never been on a carousel? Okay, that's good. I don't know the last time you're on one. If it was last week, then you should stop riding the carousel. You're too old. But eventually you get to go back on the carousel because you bring little kids with you, and that's okay. On the other hand, every time we go to Busch Gardens, there's always kids that ride the carousel. And then there's always at least one person who talks about how they got yelled at by the ride operator because they kept switching horses on the carousel. You shouldn't do that. That's bad. You'll get in trouble. There are other patrons there. So I believe this is new information for students. But if you've had a course in physics before, you may know this. If the carousel is spinning, it has what we call an angular velocity. Now that's different than a linear velocity. So far this year, velocity has been something that talks about your change in position over time. So in general, you've covered some ground. You're in a new place. So we've described linear velocity. It doesn't have to be in a straight line necessarily, but we usually talk about the fact that a linear velocity means you're moving, you're changing position, and therefore could be measured in something like meters per second. The horses on a carousel, they each have a linear velocity at this moment in this direction. Right? We would describe that as their linear velocity. They're changing position. But the carousel, it's not changing position. Right? The carousel stays in place. It's spinning. So the direction it faces is changing. Well, that's what we mean by an angular velocity. An object with an angular velocity is changing the direction it faces in some regular way. Angular velocities aren't measured in meters per second. You can probably imagine they're going to be measured in something like degrees per second. Very unlikely. I will never have a problem that's in degrees per second. But it's plausible. The most likely and the best one is radians per second. But I know just now people cringed when I said the word radians. I don't know who you are yet, but I'm going to find out. So why don't you just be honest with me and answer this question honestly? How many of you here can tell me what a radian is? Like you understand the concept of radians? I got 2 people? Okay. Raise your hand if you know why radians are unitless. Okay, then you don't understand what a radian is. The most common angular velocity, RPM. Rotations per minute, RPM. That would be the most common. In fact, it's the one I will probably use the most. So there's probably some education required here. So I want to talk a little bit about educating you guys about angular velocity, and then we'll come back to the carousel. First, I'm gonna fully appreciate this, but the fact that a circle is 360 degrees is largely arbitrary. I've heard the idea that 360 degrees was used because it was close to 365, so they used it based on like the year, and how long it takes the Earth to go around the sun. It's partially true. There's other reasons to use 360. First, you guys, it divides up nicely by 4. That's a good reason to use it. And, it also divides up nicely by 3. And since triangles are often using degrees, 360 was kind of nice to use there, right? Angles of a triangle add up to 180. There's a lot of reasons why 360 was chosen as a way of measuring angle measures. The problem is it really doesn't have any touchstone to anything else. Do you know that there's something called gradients? or gradients. Anybody ever heard of it before? It's another angle measure. Do you know what it means? You just heard about it? Gradients is often how is used to rate roadways. The gradient of the road would be the steepness of the road. It uses a percentage. 90 degrees is 100%. You can't drive on a 100-degree road. I'm sorry, 100% road. In fact, even a 50% road, which would be 45 degrees, is too steep for driving. Roads are usually a couple of percent. They don't make them very steep. That's on purpose. So 100% gradient is equal to 90 degrees. There's just different ways of measuring the same thing. You, however, have to be flexible. We're not going to use degrees when it comes to angular velocity, ever. We only use degrees for angle measures, only. Everything else in here, when it comes to angular velocity, will be rotations per minute, rotations per second, or radians per second. Everything. So 1 rotation is how many radians? If the carousel goes around once, how many radians has it gone around? 2 pi. So 2 pi radians. But radians isn't really a unit. And this part is where I'm always a little bit sad. When you were in the 3rd grade, did you figure out what pi was? This is usually a 3rd grade activity. You did it? Who else did it? Because it's a 3rd grade activity. Did you do it? A couple of you? Do you guys, if you know what I'm talking about, it probably had to do with a piece of string and something round. Do you guys know what I'm talking about now? Am I triggering your memory a little bit? Because when I was in the 3rd grade and did it, I've actually done this in high school because students have not done it. How many of you have proven pi exists? You can prove it. Just 2 of you? That's kind of sad. I'm sorry. It can be proven with calculus, by the way. You know how to get the pi to so many decimal places? They use a machine to do a Taylor expansion on something that has to do with pi. And they just do it for a lot of decimal places. But there's an easy way to measure pi. All you need is a circle. You tie a string around the outside of the circle and measure the circumference, right? Then you take a meter stick and you measure the diameter. And then you just divide those 2 numbers. And that will give you pi. It's super easy to do. And the fact that so few of you have done it is sad to me because it can be proven to students. And you can do it with anything that's circular. That's the beauty of it. This ratio exists everywhere in the universe and must be the same for all circles. It's an amazing discovery, which makes pi one of the only fundamental constants you guys have ever been taught. There's not many fundamental constants in the universe. I think 3? There's just not many. Fundamental constants have no units. They're fundamental. They are part of the fabric of the universe. This has no units because what would be the units of circumference? Probably the same as the units for diameter. So that when you divide, you get a unitless quantity. Pi's kind of amazing in that. Not to mention, in the next couple of months, you're going to see pi buried in a lot of places. It starts to come up really weird that pi shows up in so many places. In electronics, pi is everywhere, and there's no circles anywhere in any of electronics. But pi is in almost every function in electronics. It's kind of amazing to me. Now, for us, all we're talking about here is a conversion, right? Now, you may not fully appreciate what this is, but I need you to, because this part is where things matter. Circumference equals 2 pi times the radius. This is actually an equation, and I'm not sure you're aware of it, but here's the equation. Arc length equals an angle measure times the radius of curvature. A circle is just a complete, arc that goes all the way around back to where it started. But if you want to calculate the length of an arc, you can do so by multiplying how many radians you've turned through times the radius of curvature. Now, follow this for a little bit. This arc length would be considered delta x, change in position along an arc. So this would have to be a change in angle times a radius. I know you don't see where this is going yet, but you will. I'll need you to. Because here's the next one, and this one's important. If I divide both sides of this by t, then I get delta x divided by t and delta theta divided by t. I have two rates. The left side would be a linear velocity. The right side would be the angular velocity. There's a symbol that is used for angular velocity. It's Greek letter lowercase omega. It looks just like a W, a little W, with a little flare at the end. Greek letter omega. This is how you move between an angular velocity and a linear velocity. You'll notice I put a T here. That's not accidental. We talked about this T yesterday. It means tangential. The linear velocity of the horses is tangent to the curve that they're traveling along. When I go back, take a look at this picture here. The horses have a linear velocity. The problem is that the direction that they're traveling is always changing. At this instant, however, their linear velocity is that way. It's a tangent to the circle they're traveling along. So we will call this a tangential velocity. And I'll refer to tangential velocities quite a bit over the next couple of days. At the same time, the horse has an angular velocity because it's mounted to the carousel. So the horse has both velocities. It has at that instant a linear velocity, and it has an angular velocity because it's a part of the carousel. Which horse is traveling faster then? It's a trick question, but it has a real answer. If you've ever been on a carousel, you know that some horses are more exciting than others. Now, I'm not talking about the fact that some go up and down and some don't. The camels are boring, but the horses are better. The camels don't go up and down, the horses do. There's also the bench. Nobody rides the bench, unless you're like an old person, or you want to sit next to somebody that you can cuddle with. All of it sickens me. But you have your hand up, so I'll let you handle this one. Why? That's not good enough. But you're right and you're wrong at the same time. Let's see what you got.
It has to go farther in the same amount of time.
That's a great explanation. If both horses are making the same, if both horses are going around the carousel, which one will go a farther distance when they come back to their starting point? Well, certainly the one that has to make this circle is going to travel farther than the one that has to make that circle. So I'd say the outside one is traveling faster. It has a faster tangential velocity. Both horses have the same angular velocity. That's the important distinction. Since they're both mounted to the carousel has one angular velocity. But different objects on it may have different linear velocities. That's also clear from here. Right? Both horses, although mounted to the carousel, have different radii. This horse has radius 1, which is smaller than this horse, which has radius 2. Although omega is the same for both horses, the one that has the larger radius is going to be traveling faster. Not a surprise, but something I do want you to know. Now, I'm bringing this up because we're talking about uniform circular motion. So having objects that are on a spinning platform is not an uncommon style of problem. You guys who have been on any kind of spinning platform or had to walk on a spinning platform understand this a little bit. They've taken all the fun rides out of the parks for us to really play with this idea. There used to be fun rides like this. If you don't know what I'm talking about, consider one of these. It's got like a center here and something like that. They keep taking away all the good rides. Has anybody ever seen one of these? Only one of you. It makes me sad. Maybe if I draw it a little different, like if I draw it from the side, because this is top down. So if it was from the side, it would look like this. Oops, that's not pleasant. The stupid hair keeps getting in the way. Can't see anything. Does that look more like what I'm trying to make there? Yeah, so we've got those bars like that. There, has anybody seen one of these? Yeah, they take them out of parks now because, I don't know, parents can't watch their stupid kids and their kids get hurt, and therefore anything fun in life has to go, like the mall. You know, it's kind of fun. You know, get on here and then you get on here, maybe some friends get over here and they spin it and you have a fun time, right? Until you go flying off, you know, and that looks less fun. And one of the things that's important we talked about this yesterday too, if it's spinning like that and you're one of the guys that's on it, if you finally do let go, you don't actually fly off this way. Although people think that you do, you don't. At the instant that this guy's traveling right now, let's check this guy, he's going this way. This is the direction of his tangential velocity. If he were to let go, he would go that way. He looks like he's flying backwards, only to people who are also on the ride. This is the same thing about making a left turn and seeing stuff in your car shift to the right. It's not suddenly being pulled to the right. They're just going in a straight line and the car's moving out from underneath it. Same thing here. This guy doesn't fly backwards. He goes tumbling off in that direction. But because the whole ride is turning, by the time this guy sees it, he's over here, and it looked like he flew backwards. Understand the difference? You may not. You may have to go ride one of these. But you won't be able to find them because the ground is filled with, like, hypodermic needles and stuff, and they don't want you, like, to be impaled by that kind of stuff because our parks are just not as good as they used to be. So be careful, man. There's probably dog poop there, too. You'll be flung into that. Or you'll be one of the idiots who found one of these, took your motorcycle over to it, put the back wheel on it, and spun a bunch of kids until they flew off. Look at YouTube. You'll find that. Kids are dumb. Actually, it's usually adults. Adults are dumb. So, but they'll put their stupid little motorbike wheel against the edge of this, see if they can get it spinning really, really fast and see if they can launch kids or break their necks or whatever else they're doing. So yes, these things are leaving our parks, which is too bad because they're lots of fun. And the only place you'll be able to go now to enjoy them is the mall, except none of you are allowed to go anymore. So I guess you shall have no fun in life. That's our goal. Anybody ever ride on one of these? They're taking these away too. I don't know. These are a blast. You get to be my size and you get on one of these things. Oh my God, they're so fun. I love them. I went to a park a couple of years ago. I have to say years ago because I don't go to parks much like this anymore. And they replaced all the springs with posts. Not really. They just... for a thing that was a spring and it's now a post, it's not moving. It's garbage. It's just garbage. Just get rid of it. Let the kids bang sand or something. It's just terrible. Terrible. Mr. Shelton, why are we having this conversation? We're having this conversation because of bugs. Bugs. That's why we're having this conversation. I know you don't understand, but one of the... I want you to imagine I have a spider. And I used to have a spider, but we know about Lilith. We've had that conversation. Your sister knows all about Lilith. Lilith died. Lilith is gone. So, let's say I have a spider that's on a record player, and records are making a comeback now. I'm understanding I'm allowed to use records as part of my examples again. So, is there anybody in the room who is unfamiliar with what a record is? Okay, so I have a spider on a record. So we are looking straight down at the spider. And I turn the record on to one of its standard playing speeds. If you don't know the standard playing speed of a record, there's 33 and a third RPM, and there's 45s, and there's 78s, and there's 16s. But nobody uses 16s or 78s. 33 and a third or 45s are all that was ever really adopted. And even now, everything is long play, which means everything is 33 and a third RPM. All right. The spider is located 15 centimeters from the edge of the record. What minimum coefficient of static friction would be necessary for the spider to stay on the record? Say all that over again. What minimum coefficient of friction would be necessary for the spider to stay on the record? This is a tough question. Not terribly tough. Tough the first time you hear it. Because it's like, what the hell are you talking about, Mr. Shelton? Oh, I recorded that. What the heck are you talking about, Mr. Shelton? I don't know what you're talking about. You, believe it or not, have all of the details you need to answer this question. I'm not saying it's easy. I'm just saying you have the details. Let's talk about what you might have to do to solve this problem. And make sure we step it through all the things we've talked about so far this year as it pertains to force. First, is this a first law problem or a second law problem? It's got to be a second law. The only way the spider stays on the record is if they experience an unbalanced force that allows their velocity to change. Do you guys understand what I just said? Because that's an important detail. The spider does not have a constant velocity. Although they start here, after a few moments, the spider will be over here, and their velocity will have changed direction. The only way that can happen is if the spider is experiencing an unbalanced force. But in this case, it's clear to me that the spider is traveling in a circle. So when I choose Newton's second law, I'm choosing MAC. You may want to put in your decision, if the object's traveling in a circle, it's automatically a second law problem. But it's a special case of the second law problem. It's the case for an object that's traveling in a circle. Now, I still need to deal with a free body diagram. But it's going to be hard to draw that free body diagram because I'm looking top down at the spider. And I know that at least one of those forces is straight down. And one of those forces is straight up. So I'm going to, off to the side here, consider a dot that is the side view of the spider. I know the spider must experience a force towards the center. There must be some force this way. And I really think you have to be thoughtful about what might be causing the spider to not slide off of the record. But I'm trying to use words here that will cue you into what the likely force is here. What force do you guys think this has to be? You guys are so quiet. Is it because you don't know the answer, or you're nervous, or you just want to be quiet? But it's got to be friction. I've said the word slide like a dozen times, and I even used the word, coefficient of friction earlier. It's likely that the force that's causing the spider to travel in a circle is a frictional force. If the record were slippery, would the spider stay on it? I mean, ask yourself that question. So I think this is the frictional force. I don't think it's arbitrary. So I'm going to replace that with a lowercase f to remind me it's friction. So on my side view, I'm going to have friction acting sideways on the spider. But I also know that there's going to be weight and normal. Those will be the forces acting on the spider. I don't think there's anything else. Now, we've done the work here before, but I'm going to go ahead and continue. There's a coordinate system here. I'm going to make this the positive x direction. I've always said to make the acceleration the direction of positive x. I'm going to continue to say that. And I'll make this the negative y direction. it makes it pretty straightforward. So I can say net force in the x direction equals mv squared over r. Once I know it's centripetal motion, I can replace the acceleration with v squared over r. Might as well do that as early as possible. And at the same time, there's only one force there. Now the y direction's even easier because they sum to be 0, so that's just us saying normal equals mg. I know I'm skipping a few steps, but I think I'm okay to do so. Now here's where I want to add something that I did not say yesterday, but that I hinted at today. I never gave you the linear velocity of the bug, did I? I gave you the angular velocity of the record. Now, you could find the linear velocity of the bug because I've given you a way to do so. You guys see that okay? But I also want to point out something here, something that is on your equation sheet and could serve you well, speed things up. I could write this as m times omega r squared over r. I'm just doing a substitution. If I do that, you realize one of the r's is going to cancel, right? So this could be m omega squared times r instead of m v squared over r. This is a, oh my God, but he's always been great to me. I got lost in that. Let's get back to this because we're not done yet. But right now we kind of have two functions. This is what net force in the y direction gave us. This is what net force in the x direction gave us. Lots of substitutions here. I know this. And yeah, there's a lot of things. How many equations are on this next test? All of them, potentially. There's a lot. It's not about the equations, though. You'll have an equation sheet. Didn't help you last time. You have to know when to use which thing and how they're related. And we're still not even close because I asked for mu, and I don't even see it here yet. But you should be thinking about the fact that mu is an inequality. If you want to understand this question best, preserve the inequality, meaning substitute into the inequality. You'll also note that I am deathly afraid of putting numbers into my problem until the end. I don't generally, at this point in the year, put numbers in until the end. So m omega squared r less than equal to mu s m g. Part of the reason I don't put numbers in until the end are for things that you might not know until the end. Like I never gave you the mass of the spider. So you might think to yourself when you start the problem, I don't have enough information. You didn't tell me the mass. Mr. Shelton, what's the mass of the spider? I didn't tell it to you. So before you make that question out loud, do the work. And you might find that perhaps the mass doesn't matter. A lot of times it won't. Because mass is inertia and gravity, a lot of times if you have those things related, it goes away. Now we're actually solving for mu s, so you can solve for it. And I like this. You know why? Because it tells me that I'm on the right side of things. It says that my coefficient has to be bigger than or equal to a number. Mu s is how sticky the surface is. So if I want the spider to stick, I need to make sure the surface is at least this sticky or stickier. It makes sense to me. And I know where the inequality is and why the alligator mouth is eating mu and not eating the other side. I think it's important that you understand leaving the inequality gives you more information. Now, you can get an answer. There is a numerical answer to this problem. And you should look for it. You should do the work. I've given you everything you need for it. But I don't care that much about it. I do care that you guys in the room know how to go from RPM to radians per second. Who would like a refresher? Okay. I will show you how I do it. So, and I have to do it every time. I have no magic panacea, and I don't use Google. I like to do it my way. So, when I say I'm going to show you my way, I use unit multipliers. So the first thing I do is I put everything on a fraction. And over here someplace, I put what I'm trying to get, and I put what I have to start with. It looks to me like I have to convert two things. Would you guys agree that I have to convert two things? I got to convert the minutes to the seconds, and I have to convert the rotations to radians. So if I can, I try to do that with just two conversions. So I go ahead and just put in the multipliers. And I pick one to start with. For example, I'm going to pick the minutes first. I want to cancel out the minutes. So I need to put the minutes on the top because I already have them on the bottom. And whatever I put on the bottom is what I want to be left with, or what's next. So luckily this is a single conversion. I can go right to seconds right here. I put that in front of me first and then try to figure out how to use my conversion fact. There are 60 seconds in every 1 minute. So I think it's pretty easy once it's there to know where to put the 60 and where to put the 1. This way, I'm never asking myself, do I divide by 60 or multiply by 60? I never ask myself that question. I never have to. I do the same thing for the next one. I want to get rid of rotations. Rotations go on the bottom. What am I converting to? I want to be left with radians. Although not a real unit, it's always nice to have something to hold the place of where units go. Now I bring up my unit conversion. And you guys already know this. You told me that one rotation was 2 pi radians. So I know you know it. But I never have to ask myself, do I divide by 2 pi or multiply by 2 pi? And look, if any of you think I'm remotely smart, I do this every time. I write it out. Because I don't want to make a mistake that involves this. It makes you appear less capable as a person. So don't make this mistake. This one's an easy one not to make. And yeah, you can do the math now. I know you could probably do things like cross that out and make that 30. I know there's other things to do here. But I don't care that much. Get the number. The number part is the least interesting thing. Have I shown you what to do now? Do you feel confident that you don't need a refresher anymore? You can do this yourself? I hope so. Because we'll have to do this quite a bit this year. This is the only thing we convert. But we do convert angular speeds. Real quick. Yesterday I said that this is how you calculate centripetal acceleration. There's more than one way. Have them both. Have them both at the ready. If they give you angular speed, have one that uses angular speed. If they give you linear speed, have one that uses linear speed. And know when to use one or the other. Just always understand, you can only use radians per second here. Anytime omega's in a formula, radians per second is the safest way to go. So you will have to convert to radians per second. If you don't know how, I can show you.